Welcome. This is tips for assignment 3, B4 to B6. We've given, see the top right in B4, Cobb-Douglas production function Q is x to the power half, y is to the power 1/4. X and y input variables, price of each product is P, and the cost of the production function is AX plus B. So then we can write down the production function pi minus ax plus by, the cost. So that the first things we need to do is to take the two derivatives using this production function. So the pi dx is 0 and the pi dy is 0, partial derivatives, and then solve for xy, and then give the find the provided expressions. You can look in the notes, and it was essentially done in class. And then given x and y, you substitute back in pi and find the production at the stationary point, so at x star, y star. So for B, you need to calculate the Hessian from the expressions you found here, and advice is here, try to avoid substituting x star and y star. So you can, of course, you have to evaluate at the critical points, but just use x star and y star as long as possible, unless you have to substitute. But in order to draw a conclusion, you don't have to substitute. Avoid substituting for x star and y star as long as possible. And when I recall right, you don't need to do that at all in order to draw a conclusion. Okay, B5 is similar. And then you have to conclude that it's a maximum using the principal minor theorem. You only need LPM1 and LPM2. So B5, you're given now a production function of 3 variables, x, y, z, all to the power 1/4. Price 4, P is 4 per item, and the cost function of the 3 variables is x plus half y plus 1/3 z. So you in A, you're supposed to write down the production function P, and you can fill in the 4q minus c of x comma y. Of course, x comma y comma z minus c of x comma y comma z. Then you write down the FOCs. So the pi dx is 0, the pi dy is 0, the pi dz is 0. Solve for x, y, z. And in the question, just like in the notes, you first express x, y, z in terms of q, and then you can substitute that back in here to find q star, so the value of q at stationarity. And then given that you've expressed x, y, z in terms of q, you can use q to find x star, y star, and z star at the critical point. So in B, you calculate the given Hessian. Again, here you see that you can find and simplify the Hessian by using Q. You can draw conclusions whether it's a maximum based on that form of Q without having to substitute the substitute the explicit forms of Q, X, Y, and Z. So you need the LPM1, LPM2, and LPM3 in order to reach conclusions. So B6 is the water wave example in the appendix. So here the key is to realize that in the end, even though the original problem is in terms of capital X, capital Y, and tau, in the analysis, since Y is Y star is 0, you can write this as, if you wish to write it in a different way, it's only really a function of X and tau, so two variables of the function, and you are supposed to calculate the Hessian. So it's uxx, ux tau, u x tau, u tau tau. You are given the determinant of h and uxx or minus uxx in the graphs as function of a parameter, and then you're supposed to apply the principal minor theorem. So look at LPM1 and LPM2 in order to see whether we are the maximum or not, a minimum or something else. And you are supposed to tell us for which value of this parameter delta the maximum, the value at the maximum is the value at the stationary point is a maximum. So the key novelty here is that you look at the graphs in order to decide what the signs of the determinant of the Hessian and the signs of LPM1, so that's uxx, or the sign of minus LPM1 is, in order to draw conclusions. I thank you very much. That concludes it on this Saturday. Good luck with the exercises. Oh, one more remark on B2. In B2 you have double eigenvalues, so it's important in B2 that all your eigenvectors, your unique eigenvectors, are orthogonal to one another. So for the double eigenvalues, you can find two vectors which satisfy the eigenvector equation. But any linear combination of those vectors will also satisfy the eigenvector equation, and you are supposed to seek two vectors which are orthogonal to each other, but also orthogonal to the other eigenvector belonging, associated to the eigenvalue, the single eigenvalue, so the unrepeated eigenvalue.